Hello everyone, hope you are all doing well. In this video, I will be discussing the answers for in-text questions of NCERT Class 12 Chemistry, Chapter 3 Chemical Kinetics. Question number 3.1. For the reaction R to P, the concentration of reactant changes from 0.03 molar to 0.02 molar in 25 minutes. Calculate the average rate of reaction using units of time both in minutes and seconds. So the reaction is R is changing into P. They have given us concentration of the reactants in two time intervals T1 and T2. So at T1, let us consider the concentration as R1 and that is equal to 0.03 molar. At time interval T2, let's consider the concentration of R as R2 and that is equal to 0.02 molar. So now they told this change is taking place in 25 minutes and we have delta T, that's nothing but T2 minus T1, which they have given us as 25 minutes. We need to calculate the average rate of the reaction. So we have average rate is equal to minus delta R, that is change in concentration of the reactants, divided by delta T, and this is equal to minus of R2 minus R1 divided by delta T. This is equal to minus of R2 is 0.02 molar, R1 is 0.03 molar divided by delta T, that is 25 minutes. Subtracting 0.03 from 0.02, we get minus 0.01 molar, which has to be divided by 25 minutes. So now minus into minus will become plus. We have to divide 0.1 by 25. So dividing 0.01 by 25, we get the answer as 4 into 10 to the power minus 4 and the unit is molar per minute. So we have calculated average rate in the units of time, that is in minutes. Now we need to calculate it in terms of second. Now let's do it. We know that 1 minute is 60 seconds. So I can write 1 minute by 60 second is equal to 1. So using this unitary method, we will convert now the unit in terms of minute inverse to second inverse. So what you have to do is, we will multiply the R average with 1 minute by 60 second. So it's 4 into 10 to the power minus 4 molar per minute into 1 minute divided by 60 second. This is equal to 4 into 10 to the power minus 4 divided by 60. Minute per minute it cancels with one another. So we have molar and the second will go to numerator, that becomes second inverse. So now simplifying 4 divided by 60, we get 0.0666 into 10 to the power minus 4 molar per second. So I can write this as 6.66 into 10 to the power minus 6 molar per second. So here we have average rate in the unit of time, that's in second. Question number 3.2. In a reaction, 2A given products, the concentration of A decreases from 0.5 mole per liter to 0.4 mole per liter in 10 minutes. Calculate the rate during this interval. So they have given us the reaction 2A is getting converted to products. So they told concentration of A is decreasing from 0.5 mole per liter to 0.4 mole per liter in 10 minutes. So at time t1, concentration of A is A1 and that is given as 0.5 mole per liter. At time t2, concentration of A is A2 and that is 0.4 mole per liter. So they have given this change in concentration, that is decrease in concentration of A is taking place in the time interval of 10 minutes. So delta T is 10 minutes. And we are asked to calculate rate during this time interval. So from this equation, 2A giving products, we can write rate is equal to minus 1 by 2 into delta A, that's change in concentration of A, divided by delta T, that is change in the time, or T2 minus T1. So substituting, we have minus 1 by 2 and change in concentration of A is A2 minus A1 divided by delta T. Substituting, minus 1 by 2, concentration of A at T2 is 0.4 mole per liter minus at T1 it is 0.5 mole per liter. So unit I will be writing together, divided by delta T and that is 10 minutes. Simplifying this, minus 1 by 2, 0.4 minus 0.5 is minus 0.1 divided by 10 and the unit will be mole per liter per minute. So this is equal to minus into minus, that's plus 0.1 divided by 20 mole per liter per minute. So 0.1 divided by 20, that's equal to 5 into 10 to the power minus 3 mole per liter per minute. And this is the answer for rate of the given reaction. Question number 3.3. For a reaction A plus B giving products, the rate law is given by R is equal to K into concentration of A raised to half into concentration of B raised to 2. What is the order of the reaction? So we are asked to find order of reaction. For a general reaction, A plus B giving products, that's P. If we write the rate expression, we write R is equal to K concentration of A raised to X into concentration of B raised to Y. For this rate law, we can write order is equal to X plus Y. It is the sum of the powers of the concentrations that's raised in the rate law. So now they have given us the rate law is R is equal to K concentration of A raised to half concentration of B raised to 2. So here X is half, that's 1 by 2 and Y is equal to 2. So therefore we have order of the reaction that's equal to X plus Y, which is equal to half plus 2. So it's 2.5 or 2.5. So order of the reaction is 2.5 or 2.5. Question number 3.4. The conversion of molecules X to Y follows second order kinetics. If concentration of X is increased 3 times, how will it affect the rate of formation of Y? So they have told that conversion of molecule X to Y is second order kinetics. Therefore, I can write rate R is equal to K into concentration of X raised to 2. So since it's a second order reaction, concentration of X is raised to 2. So now they have given us that concentration of X is increased to 3 times. So now concentration of X will become 3 times the concentration of X. Okay, substituting this into the rate law, I can write R prime, which is equal to K into 3x squared. So this will become 9 into K concentration of x squared. So we know this K into x squared is the initial rate. So I can write R dash is equal to 9 into R. So clearly you can see that when concentration of x is increased by 3 times, we see that rate is increased by 9 times. So I can write that rate is increased 9 times. So this is the answer for this particular question. When the concentration of X is increased by 3 times, rate of the reaction will be increased by 9 times for the given second order reaction. Question number 3.5. A first order reaction has a rate constant 1.15 into 10 to the power minus 3 per second. How long will 5 gram of this reactant take to reduce to 3 gram? So they have given us the rate constant for first order reaction. First of all, we shall write the expression for rate constant of a first order reaction. That is, we have K is equal to 2.303 divided by T log of R naught divided by R, where R naught is the initial concentration of the reactant and R is the concentration of reactant at a time interval T. So the rate constant they have given us, it's 1.15 into 10 to the power minus 3 per second. Time is what we need to calculate. They have given us the concentration is reduced from 5 gram to 3 gram. We need to calculate what is the time taken for that. So R naught is 5 gram and R will be 3 grams. Now substituting all these values into the expression for the rate constant, we have 1.15 into 10 to the power minus 3 per second is equal to 2.303 divided by T, that's what we have to calculate, log of R naught, that's 5 gram, divided by 3 gram. Gram and gram gets cancelled with one another. So I can rearrange this and write T is equal to 2.303 divided by 1.15 into 10 to the power minus 3 per second into log 5 divided by 3. Simplifying this, 2.303 divided by 1.15, that's equal to 2.002, I'll consider it as 2, into 10 to the power minus 3 when goes to numerator, that will become 10 to the power plus 3, log of 5 by 3, that is 1.1667, and the unit per second which is in the denominator, when it goes to numerator, the unit will become second. So we need to find 2 into 10 to the power 3 into log of 1.6667. So this log value you need to find using log table. So the value of log 1.1667 is 0.2218. So multiplying this with 2 into 10 to the power 3, we get the answer as 443.71. So this approximately we can consider this as 444 seconds. So therefore, the time required for the reactant to reduce from 5 gram to 3 gram is 444 seconds. Question number 3.6. Time required to decompose SO2Cl2 to half of its initial amount is 60 minutes. If the decomposition is a first order reaction, calculate the rate constant of the reaction. So they told us that the decomposition reaction is a first order reaction, and we know the relation between half-life and rate constant for a first order reaction is T half is equal to 0.693 divided by K. So here we need to find rate constant. So rearranging this expression, I can write rate constant K is equal to 0.693 divided by T half. So in the question they have given us the time required for decomposition of SO2Cl2 to half of its concentration. It is 60 minutes. So T half is 60 minutes. So now we can calculate the rate constant, that is 0.693 divided by 60 minutes. So dividing 0.693 by 60, we get 0.01155 unit is per minute. But we know for a first order reaction, rate constant is expressed in terms of per second. So we need to convert this value in seconds. So we know that 1 minute is equal to 60 seconds. So by using unitary method, since I need to convert minute inverse to second inverse, I'll write 1 minute by 60 seconds is equal to 1. So to find the unit of K in terms of second inverse, I'll multiply the answer 0.01155 per minute into 1 minute divided by 60 seconds. So minute and minute inverse gets cancelled. Now I have to divide 0.01155 by 60, and this comes out to be 1.925 into 10 to the power minus 4, and the unit is second inverse. So therefore the rate constant here is 1.925 into 10 to the power minus 4 per second. Question number 3.7. What will be the effect of temperature on rate constant? So here you need to write the answer in the descriptive way. I'll just write down the points here. So we know that for every 10-degree rise in temperature, rate constant is doubled. So this is what is the effect of temperature on the rate constant. For every 10-degree rise in the temperature, rate constant of a reaction is doubled. And this relation is quantitatively told by Arrhenius equation, which is written as K is equal to A into e to the power minus EA divided by RT. Here in this expression, we have K is the rate constant, A is Arrhenius constant, or it is frequency factor, EA is energy of activation, or it is activation energy, and we have R, which is gas constant, whose value is equal to 8.314 joule per Kelvin per mole. And we have T, that is temperature. So these are the things that you need to include to answer. Temperature is going to affect rate constant of a reaction. Question number 3.8. The rate constant of a chemical reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. Calculate energy of activation. So we are asked to calculate activation energy, and they told that the rate of chemical reaction doubles for increase in 10 Kelvin. So they have given us one temperature T1, that is 298 Kelvin. And they told that temperature is increased by 10 Kelvin. So we have temperature T2, that is 298 plus 10, which is 308 Kelvin. So they told that rate of the chemical reaction doubles after that. So if we consider rate constant as K, so I write K1 as K. After 10 degree rise in the temperature, if suppose I consider rate constant as K2, the rate will be twice, so rate constant is written as 2K. We are asked to calculate activation energy. Using the formula log K2 by K1 is equal to EA divided by 2.303 R T2 minus T1 divided by T1 into T2. Now let us substitute all these values into this particular formula. So we have log K2 is 2K, K1 is K, so it is 2K divided by K, which is equal to EA divided by 2.303 into R, that's 8.314, into T2 minus T1. So T2 is 308 minus T1, that is 298, divided by 308 into 298, that's T1 into T2. So here K and K gets cancelled. So we have log 2, that is equal to EA into 308 minus 298 is 10, divided by 2.303 into 8.314 into 308 into 298. So we need to determine EA. So let me rearrange this expression. EA is equal to log 2 into 2.303 into 8.314 into 308 into 298 divided by 10. We know log 2 is 0.3010. Now let's multiply every term in the numerator and let's divide it by 10. So we have 0.3010 into 2.303 into 8.314 into 308 into 298 divided by 10, which is equal to 52,897.778. So I'll write this as 79. This is in terms of joules per mole. So this I can write as 52.879 into 10 to the power 3 joules per mole, that is equal to 52.8977 kilojoules per mole. So this is the answer for activation energy for the given reaction. It's 52.8977 kilojoules per mole. Question number 3.9. The activation energy for the reaction 2HI giving H2 plus I2 is 209.5 kilojoules per mole at 581 Kelvin. Calculate the fraction of molecules of reactants having energy equal to or greater than the activation energy. So we know that the fraction of molecules which have energy equal or greater than activation energy is given by e to the power minus EA divided by RT. So let me consider this fraction of molecules as X. Okay, so X is equal to e to the power minus EA by RT. I'll write X is the fraction of molecule which have energy, having energy greater than or equal to activation energy. To find the value of X, I need to simplify it. So I'll take natural log on both sides. So taking natural log on both sides, I can write ln X is equal to minus EA divided by RT. So I'll convert this into logarithm. Okay, so I can write this as log x is equal to minus EA divided by 2.303 RT. So I'm substituting activation energy, they have given it as 209.5 kilojoules per mole. So minus of 209.5 kilojoules per mole divided by 2.303. R is 8.314 joule per Kelvin per mole into temperature, that's 581 Kelvin. So unit of gas constant is joule per Kelvin per mole. So this mole inverse gets cancelled. Per Kelvin, Kelvin, so both are present in denominator, gets cancelled with one another. So here in the numerator we have it as kilojoule. So converting that into joules, I can write minus 209.5 into 10 to the power 3 joules divided by 2.303 into 8.314 into 581, which is equal to 11,124.4895. So log x is equal to, simplifying this, minus 209.5 into 10 to the power 3 divided by 11,124.4895, which is equal to minus 18.8323. So log x is equal to minus 18.832. In order to find the value of x, let us take antilog. So it's antilog of minus 18.8323. So finding the antilog of minus 18.8323, we will get it as 1.47 into 10 to the power minus 19. So therefore we have 1.47 into 10 to the power of minus 19 fraction of molecules whose energy will be more or equal to that of the activation energy. Thank you for watching. If you have not watched our NCERT classes, you can watch those videos by clicking on the playlist here. I'll meet you in the next video. Take care. See you. Bye-bye.